The vast hall stands in near silence. It is a cavern of polished concrete and steel, empty under the cool, even glow of overhead lights. Then, a single light on a robotic arm blinks from amber to green. A low hydraulic hiss follows as the arm unfolds. Its multi-jointed limb moves with a grace that belies its strength. Across the hall, another machine answers. Conveyor belts begin to glide. A symphony of precise, mechanical sounds builds. This is the factory of tomorrow, and it is waking up. It is a place that can run almost entirely on its own. A complex ecosystem where machines, guided by intelligent software, perform the intricate dance of modern manufacturing with minimal human intervention. The core idea is both simple and profoundly transformative. It is the notion that a physical production facility can be managed like a piece of software. Its operations can be coded. Its performance can be monitored in real time. Its processes can be optimized automatically. This is not science fiction. It is the culmination of decades of progress in engineering and computer science. The machines are the muscle. The true innovation lies in the nervous system connecting them. This system gathers information, makes decisions, and coordinates actions with a speed and precision that humans simply cannot match. The goal is not to remove people. It is to elevate their role from performing repetitive tasks to designing, supervising, improving these highly complex, self-sufficient systems. This quiet revolution is unfolding in pockets around the world. It is driven by a need for greater efficiency, higher quality, more resilient supply chains. In an autonomous factory, production can continue 24 hours a day, 7 days a week, with pauses only for planned maintenance. Errors that might lead to defects are caught and corrected in milliseconds, not hours. The entire facility can be reconfigured to produce a new product with a few lines of code, rather than weeks of manual retooling. It represents a fundamental shift in how we think about making things, moving from a process reliant on manual labor to one orchestrated by data and intelligence. The scene, though devoid of a human crowd, is far from lifeless. Every movement is deliberate. Every action part of a meticulously planned sequence. An autonomous guided vehicle glides across the floor, carrying raw components to a production cell. A 6-axis robot arm picks up a component. Its vision system identifies the precise orientation needed. It places the part into a milling machine. The door closes. The process begins. Each step is recorded, each variable measured. This is not just automation. This is orchestration, a carefully choreographed ballet of machines, all working together towards a common goal, guided by an unseen intelligence that resides in the digital realm. The push towards the autonomous factory is not a sudden development. It is a logical next step, accelerated by the convergence of several powerful technologies. For decades, factories used rigid siloed automation. Robots did single repetitive tasks and couldn't adapt. Today, it's different. Ubiquitous sensors, powerful artificial intelligence, advanced robotics, and high-speed data networks together create true, flexible autonomy. Sensors are smaller, cheaper, more capable. Sensors embedded across the production line measure temperature, vibration, and exact dimensions to microns. That stream of information is the factory's lifeblood. It feeds AI to learn, predict, optimize. Without real-time data, the factory would be flying blind. High-speed networks, 5G, fiber optics, move massive data from the factory floor to processing centers. Robotics has evolved. Today's robots aren't the caged brute force machines of the past. They have advanced vision systems, force torque sensors, giving them sight and touch. They perform delicate assembly, adapt to part variations, and work safely alongside humans. Programming is more intuitive, taught through demonstration or optimized via AI-driven simulation. Flexibility lets factories switch products quickly. Mature AI, especially machine learning, manages the complexity. AI predicts failures, predictive maintenance, inspects finished products with superior consistency, analyzes the whole production system, finds bottlenecks, and suggests improvements. Learning and adaptation distinguish autonomous from merely automated. The system improves over time, becoming more efficient and reliable with every product it makes. To understand a fully autonomous factory, It is best to think of it not as a single entity, but as a collection of interconnected subsystems, each with a specific role. At its heart, a fully autonomous factory is a manufacturing facility where nearly all operational tasks, from receiving raw materials to shipping finished goods, are executed and managed by automated systems with limited, high-level human oversight. It is a system of systems, where physical machinery and digital intelligence are fused into a cohesive whole, self-configuring, self-monitoring, self-optimizing, capable of responding to new orders and unexpected disruptions with agility. The first and most visible subsystem is the production line itself. Robots, computer numerical control machines, 3D printers, automated assembly stations. These are the hands of the factory. Each piece of equipment is embedded with Internet of Things sensors that constantly report on its status, performance, and environment. This layer is designed for modularity and flexibility. Cells reconfigured via software commands. Robots automatically swap end effectors, changing from a gripper to a welding tool as needed. The second subsystem is the Central Control AI, the factory's brain. Not a single program, but a suite. MES managing real-time workflow, ERP handling order management, inventory and supply chain coordination, and machine learning models for predictive analytics, quality control, and process optimization. This AI brain integrates information from all subsystems to make holistic, data-driven decisions. The third critical subsystem is the digital twin, a complete, high-fidelity virtual model of the entire factory. It is a dynamic simulation continuously updated with live data from IoT sensors. It serves as a risk-free sandbox to test new processes, simulate failures, or train AI before real-world deployment, and provides a comprehensive visual interface for human supervision. We will explore this concept in greater detail later. The flow of data in an autonomous factory is a continuous, circular journey, starting with a physical event and ending in a refined, intelligent action. At the edge, a thermocouple on a conveyor motor becomes a digital value. It is time-stamped and tagged. An edge device runs local rules, logging normal ranges but instantly alerting and slowing or stopping a conveyor on a sudden spike in milliseconds. The MES aggregates temperature with thousands of other signals, correlating it with production speed or load, surfaces it on dashboards, and logs it for traceability. In the cloud, years of fleet data train models to learn subtle precursors of failure. The AI may estimate a 90% probability of motor failure within 72 hours. That prediction becomes actionable intelligence sent back to maintenance planning to schedule replacement, turning a raw temperature reading into a proactive, intelligent action. In an autonomous factory, intelligence extends to the entire logistics chain. The ERP connects directly to suppliers. When microchip inventory drops below threshold, a purchase order is sent automatically, based on inventory, production forecasts, lead times, and shipping costs, to ensure just-in-time arrivals. Inside, AGVs and AMRs move materials, self-driving trucks dock, robotic arms unload, dense automated storage retrieves bins. Signals from production summon parts. AGVs deliver directly to stations. Work in progress flows automatically between cells. The MES choreographs timing so each station receives parts exactly when ready, creating one-piece flow. After assembly, products are inspected, packaged, palletized, and transported to shipping. The logistics system optimizes routes, analyzing cost, transit time, weather, and port congestion to determine the best delivery plan. A self-driving truck is scheduled and loaded. Its journey is tracked in real time, feeding data back into planning for the next wave of shipments. The shift to fully autonomous factories brings significant economic changes and has profound implications for the workforce. The primary economic driver is a dramatic increase in productivity and efficiency. A factory that can run 24/7 with minimal downtime, with a near-zero defect rate, can produce goods at a much lower cost per unit. This is not just about replacing labor costs. It is about optimizing the use of expensive capital equipment, reducing energy consumption, eliminating waste from scrap and rework. These savings can make manufacturing viable in high-wage countries, potentially leading to reshoring. However, the initial investment is substantial. Advanced robotics, sophisticated software, and digital infrastructure, creating high barriers to entry favoring well-capitalized firms. New models are emerging, factory as a service, where companies rent production capacity from shared autonomous facilities, letting smaller businesses access advanced manufacturing without huge upfront cost. The impact on the workforce is complex. Jobs centered on repetitive manual tasks, assembly line work, and manual material transport will decline. Machines can perform these tasks more safely, quickly, and consistently. This displacement is a real social and individual challenge. Yet autonomous factories also create and transform roles. Robot coordinators, AI trainers, digital twin engineers. These roles require data analysis, software development, and systems thinking. Maintenance technicians who once used wrenches and grease guns must diagnose sensor networks and work with robotic software. Human work shifts from doing to thinking and supervising. Governments, companies, and educational institutions must invest heavily in reskilling, designing, managing, and improving future factories. The change is not a future without jobs, but a future with different jobs. Fully autonomous factories weave robotics, AI, digital twins, IoT, and logistics into a single operational fabric, measured, reliable, and continuously improving. The path is practical: instrument, connect, simulate, learn, and iterate. Start with data and visibility, layer in AI for quality and maintenance, then expand to logistics and full closed-loop optimization. If you design, invest in, or operate production, now is the time to build the digital foundations and pilot autonomy where it matters most.